make very, very welcome in the time-honoured tradition of banging your hands together quickly and loudly. Please make welcome Dr. Sabin Zahirovic.
Thank you, folks. Chris, I mean, what can I say? It's incredible. I have a lot of things to say about you, and I'll save it. I have a few slides for that. But I think actually the MVPs, the most important people, are actually here. And, you know, I think teaching for me is an extraordinary honor and privilege, because in this very classroom, I have a class in here with 480 students. And, you know, it gets packed out. We have a lot of fun. But every few years, these students, they come back to me after being, you know, out in the wild. And they come back and they're just telling me the incredible things that they're doing. They're flood forecasters, they're working in the United Nations, they're changing the world for the better. And all of you, I think, are going to be doing amazing things. So we're going to be keeping close eye on all of you. But look, let's get into some of this, and we'll have discussions. And so today I just wanted to talk about, I guess, how I see earth science as a really important vehicle for trying to also make the world a better place. It's also fun. For example, this is the Madsen building where I have my office, or I live, whatever you want to call it. And you see the sandstone, Sydney's famous sandstone called the Hawkesbury sandstone. And geology, or earth science, helps us understand nature's time capsules, right? So what we have in here, inside the sand, tiny grains of zircon minerals. And we can figure out their ages. And what we can figure out is that they likely came all the way from the Ross Mountains in Antarctica, when Australia was still part of Gondwana, the megacontinent. So we had rivers as big as the Amazon transporting sediments from those mountains to here. So we have interesting, cool, fun stories like that. But we also have the ability to enact change. It could be to mitigate, understand natural hazards, climate change, food, water, energy security, and a lot of other things. So let's get into it. But before I begin, I want to acknowledge that we are in a very special place where learning and exchange of knowledge has occurred for tens of thousands of years. So I want to pay my deep respects to the Gadigal people of the Eora Nation, pay my respects to their elders, past, present, and emerging. So very fortunate to be here. So I come from the School of Geosciences across the road. We deal with geology, geophysics, environmental science, geography, marine science, coastal studies, sustainability, and we have people also working with EVA in terms of Earth observation using CubeSats and remote sensing and so on. But look, I just wanted to introduce, I guess, myself, my journey. I was born in the former Yugoslavia in 1986, and I became a child refugee in 1992. This is a house. I was in the basement when an air raid struck that house, and you know, pulled from the rubble, almost didn't make it. And you know, there were 4 years of this sort of stuff and lots of other things which we can talk about. I think it's important to talk about it because the world is a messy place. The world is a difficult place. People around the world live in poverty. People in Australia live in poverty. And so I'm trying to be the voice of those people and try to use science as a vehicle to enact some change, right? And there's lots of ways that we can do that. But during the war, this is the basement. This is you know, after the war. You can see the bomb actually penetrated the concrete barrier. It injured one of the people in the basement. It killed the neighbor who was chopping wood, and there were lots of casualties next door in a maternity ward, unfortunately. But yeah, the world is a messy place, and one of the things I did have in that time, we didn't have electricity, we didn't have running water, didn't have medicine, but I had one book which was a planetary science book, and I think that's something that was my little escape from the air raids and the various things happening around me. But look, what war and violence and hate can destroy, love and kindness can rebuild, and in a much better way. But we shouldn't have to expend all this energy unnecessarily, all this effort, and waste human life and potential. Anyway, I came to Australia in '97 as a refugee, didn't speak a word of English. I finished high school in 2005. I liked science, but it was actually my worst mark. So I was like, I'm a sucker for punishment, and, ended up doing science. I do love it, don't get me wrong. I was, first in family. I had no idea what I was doing. I actually started in IT and engineering and disliked both, and had an elective in geology. But it sparked in me, whether it's that book, Planetary Science, that I had as a kid, as a refugee, but also this deep resonance that we can use earth science and other science to try to solve some of the challenges in the world. So I switched my major to geology, geophysics, and geography, finished undergrad. It was a global financial crisis. There were no jobs. But then I kind of fell into honors, a PhD, and have been doing research, which I'll talk about. And look at this. This is from actually 2005. Do you? Can you? Yeah. Yeah, that's true, actually. No facial hair. I've aged a lot. Chris hasn't. I don't know what his secret is. But what Chris taught me, most importantly, other than the amazing science that we did, but that you can do science with kindness, right? That you can bring humanity back into science. It's not just numbers. You can actually do things with respect and love of humanity and try to improve things. Now, so, I went into geology, and the traditional view of us is that we like to lick rocks and whatnot, and occasionally that does happen. Because of the COVID restrictions, we tell the students not to lick rocks anymore, because that's not great. So look, I've certainly had my fair share of being out collecting rocks. So here, one of my other amazing mentors is Lisa Morgan. She's a USGS geologist, and here we are on top of this Yellowstone supervolcano. But actually, most of my time is in front of the computer, okay? So building models of Earth through time, and I'll introduce you to those. So the bread and butter of my research, and it's branching out a lot, but it's in plate tectonics and paleogeography. So these are numerical models of Earth, and I'm trying to understand how does plate tectonics drive the planetary carbon cycle? What does that mean for planetary habitability through time? But maybe, how can we also use these models to help us reach net zero carbon emissions and, the net zero targets and the renewable energy transition, which I'll talk about a little bit later. Who's ever seen this very specific map? Okay, who knows the significance of this very map? Yep.
Does it show the ring of fire?
So it does show the ring of fire, yes, but that's not specifically. Yeah, correct. Tectonic fault lines. Okay, yes, that's true. Yes, but there's something a bit more specific. Elevation. Okay, so this is a map, a hand-drawn map. It's the first map of the Earth that includes seafloor, okay? The oceanic topography. And that was handmade by Marie Tharp. There's Marie Tharp. She did it by hand by looking at echo sounders from ships that were crisscrossing the Atlantic and the Pacific. She was completely overlooked in her observations, which, as someone mentioned, you had these deep trenches, these subduction zones, we call them, and then the submarine mountains, which we call mid-ocean ridges. And she suggested to her colleague, Bruce Heesen. It's like, wow, Bruce, this looks like evidence for, continental drift. There's motion here, there's earthquakes. And Bruce Heesen replied, he said, oh, and I quote, "Oh, Marie, you're enough trouble already. This is just girl talk." Okay. And so just that one comment and this perception held back our science by at least a decade. And I use this as an example of how cultural constructs can really hold us back. Okay. So Marie Tharp discovered a huge, chunk of the evidence that we needed for plate tectonics. And of course, we still do Marie's work using vessels like this. And there's a picture of Marie Tharp. Here's my friend Sarah, who's an artist and a geoscientist. And I'm very lucky to have a copy of this artwork. It's incredible. So Marie Tharp was really instrumental in us understanding the Earth. And what I'm going to do is I'm going to pass around a 3D globe that I've printed. And hopefully you'll be able to feel, the mid-ocean ridges, the seamounts. And I've got some hand sanitizer too, stay COVID safe and whatnot. But apparently, yeah, whoever asks the most insightful question, according to Chris, will get to keep this globe today. I have another one for tomorrow, so let's pass that around. Okay, so, and someone mentioned here as well, of course, Marie Tharp had overlain the location of earthquakes. This is what you see in green. And this is what we call the plate boundaries, okay? Earthquake activity, volcanism, and so on. And so this is our current understanding of plate tectonics, which is, again, what I look at in great detail and through time. We have a terrestrial planet. And we have a few things about this planet that make it quite interesting. Well, first, we have life. We also have plate tectonics. And we have what we call a rocky mantle. Okay? Now, rocks are terrible conductors of heat. If you go to the beach on a sunny day, on a hot summer's day, you might actually burn your feet, right? But a centimeter down, it's cool sand, right? So it's same principle in the mantle. You have rocks that are very poor conductors of heat. And the most effective way for that heat to be lost to space is through convection, okay? Moving hot things up to the surface through buoyancy, and then they cool, and eventually they'll also sink back down when they cool through subduction. And so the inner core is about 6,000 degrees Celsius, which is the same temperature as the surface of the sun, okay? And this is what drives convection, and I would argue it's some of the key components of the life support system on our planet, okay? Now, plate tectonics was this unifying theory in Earth science that simplified everything, brought things together. I've since published with evolutionary biologists looking at the evolution of pigeons through the lens of plate tectonics and so on. But what it allowed us to do, it's the equivalent of this paradigm shift from an Earth-centric to a sun-centric view of our solar system. Just simplified a lot of things and explained a lot of things. So that's what plate tectonics did for us in Earth science. So these are the plate tectonic reconstructions that I make. This is the last 150 million years. And you'll see Australia was part of Gondwana, and Gondwana split up, and Australia has been going north. We're currently moving at about 7 centimeters a year. As we crash into Southeast Asia, that's where the earthquakes and so on go. Whoa, that's animation's going a little bit crazy there. But one of the key things is that this software is open source. It's what we develop here at Sydney Uni. And I feel very strongly about this, that it's an important component of democratizing science. Again, a way that we can improve accessibility to STEM around the world is by making things open, well-documented, and really easy to use. I can then run mantle convection models. So you see all the blue stuff is the cold subducting plates, tectonic plates, and as they sink, they sweep up the hotter material, and you get upwelling. At the edges of these upwellings, you get the mantle plumes. Who's been to Hawaii or Iceland or Michelle at the back? A few people at the front here. So that you can see these hot plumes in red rising. We can then validate these models, forward predictions, using earthquakes to image the Earth's interior and double check that our models are making sense. So we can iterate through that, given that the geological record is patchy, okay? And there's a lot of detail that I don't want to get into that, you know, sometimes in geology we just have to say, look, we have no clue what was happening at this time because there was no rocks, there was no time capsules recorded at that time. So here's just another view, a sweep through the Earth's interior, through Southeast Asia, and you can see these blue things represent subducted tectonic plates. They're cold, and then you see in orange the hotter material that's upwelling, you kind of see the 3D structure of Earth's interior. From these convection models, it tells us something about, well, what happens to the surface of the Earth. When things sink in the Earth's mantle, it drags the surface down. We call this dynamic topography. And really the main thing to take away from this is that there are red areas which have, you know, dynamic upwellings and blue areas which are dynamic downwellings. And one of the things that most people don't realize in Australia is that our whole continent is tilted slightly to the northeast because of this process. Okay? So our southern continental margin is actually quite narrow, and our northern continental margin is very wide and shallow, flooded continental crust. And so more recently, so we're trying to build this whole Earth system. This is hot off the press. This is just us post-processing some model output. So we're trying to link the deep Earth with the surface. And so I'm just going to point out here, this is how many millions of years ago. So this is 2 billion years ago. Okay? This is the arrangement of the continents. 2 billion. That's as far as it can go back at the moment, Chris. Which is, you could say it's fantasy. But you know, what we've got is, again, open source community software tools that we've improved upon. And it predicts ice cover, winds, ocean currents, precipitation, temperature, sea surface temperature, salinity, upwelling, downwelling in the oceans, and so on, right? So we're kind of creating a time machine that we can test with the geological record as well. And this is what it looks like, this animation. You see the dance of the continents. They bounce around. And we can track that through time in these climate simulations. So we can explore the past of the planet, which has implications also for the future, which I'll talk about in a moment. So we're trying to build these whole Earth community open source models that include mantle convection, you know, this dynamic topography, the plate tectonics, and the climate, so hydrosphere, atmosphere, cryosphere, and even aspects of the biosphere. So the climate modelers, we ask them, like, you know, is there a way that we can just turn off vegetation? I'm like, why would you do that? Are you crazy? Like, we're like, well, before 400 million years ago, there were no land plants. There was no vegetation before the Devonian, and so we actually want to turn it off. I'm like, oh yeah, okay. So you know, it's really important to incorporate these sorts of things because it affects the albedo and whatnot. We can look at the paleogeography and then create these living, breathing maps of Earth evolution, right? That include landscape processes, so erosion, deposition, flooding of continents. And this is used in a lot of ways in evolutionary biology and all sorts of fields. But the key, again, is that we're democratizing access to these things, right? Just the tectonic software, it was previously about like $10,000 US per license per year to have something like that. And my colleagues in the developing world just don't have that sort of money. So they just get it now for free, which is really good. Okay, so tectonic processes like volcanic degassing of CO2, water vapor, they've changed the composition of the atmosphere, hydrosphere, water chemistry, and so on. And this, of course, has implications for planetary habitability and natural variations in climate, which we can now start exploring with these climate models. And just to give you an idea that in the Earth's interior, we think there's about 3 times the volume of the ocean's water locked up in the minerals within the mantle that can be liberated through volcanic processes. So even the hydrosphere that we're taught at high school, there's a deep part of that water cycle. And I'll talk about the deep carbon cycle tomorrow specifically. Now, what you see here is a volcano, cross-section of a volcano, and then in the volcanic plumbing system you have magma, sorry, I can't believe I just said lava, but it's a Monday afternoon, magma. And then, you've got things like gold, copper, and other things that might form in there. So you can use these tectonic models as well to predict where you might have copper deposits. And given the urgency of the energy transition, well, these models might help you reduce the environmental footprint of exploration for these things. And we'll talk about that a little bit. But let's just touch on some of this deep carbon cycling. So Mount Etna, which you see here, emits about 5.8 million tons of CO2 per year. And all volcanoes on Earth emit about 645 million tons. And lots of climate change skeptics say, oh, well, climate change, it's all just driven by volcanoes. They're just erupting and, but they've been erupting for a long period of time, and it would be very convenient that since 1950, suddenly we have an acceleration of warming. And Eunice Foote, she figured this out a long time ago in 1857, essentially saying that, well, CO2 is a greenhouse gas. And could lead to warming in sufficient quantities in the atmosphere. Here's a little article from New Zealand in 1912, essentially saying that as we burn more coal, we liberate huge amounts of CO2, and over time, this effect may be considerable in a few centuries. So we started to become more aware of the carbon cycle on our planet and the human contributions to that carbon cycle. And of course, just talking about the carbon cycle, we've got our planet, it's got plate tectonics, and it's got this interesting two-way carbon cycling, right? Carbon can come out through the volcanoes, but it can actually be returned back into Earth's interior. Venus has essentially a one-way carbon valve, so it's got a runaway greenhouse effect. And Mars does not have tectonics or mantle convection, so there's not much really going on there at the moment. And these perturbations to the carbon cycle have driven wild swings in climate in deep time. So for example, these are what we call the snowball Earth episodes. We have geological evidence that the ice caps actually met at the equator. So we had a runaway ice house. And the only way that that was broken was actually through volcanism, poking through the ice, filling the atmosphere with CO2, and melting that ice. And then we have the flip side. We have greenhouse climate states where we have no permanent ice sheets, like the Cretaceous, 100 million years here in Antarctica. You actually see, this is, of course, an artist's depiction. We have petrified or fossilized wood. Essentially like temperate forests in Antarctica at the time. So much, much warmer conditions. And we've had these swings. So this is like from 540 million years to the present. So we've had periods of warm and cool and warm and cool. And so we can use these models to try to reconstruct what the past state of the climate was, carbon cycling. And we can look at these perturbations that I mentioned, because that's what we're doing right now. Since industrialization, we are unlocking deep reserves or reservoirs of carbon that have been buried by nature, by the geology, in coal deposits, oil and gas, and so on. They've been sequestered there for hundreds of millions of years, and we're now burning those, and they're ending up in the atmosphere. And this happened also in geological time, in occasion. So this is the end Permian mass extinction, when we had this massive mantle plume erupting over Siberia over just a couple of millions of years. And it brought a whole bunch of carbon dioxide from the deep mantle, but also ignited a lot of buried coal seams and liberated a lot of CO2 from limestones and so on. But what we had here is that this is the closest we came to losing the entire biosphere on our planet, okay? We almost lost all life, but 95% of marine species went extinct. And again, about the last 500 or so million years, this is the end Permian mass extinction. Now, there have been 5 great mass extinctions, and guess what? We're in the 6th great mass extinction right now, again driven by carbon cycle perturbations on our planet. And so we, as part of our work with the Deep Carbon Observatory, we were going to around the volcanoes. So this is Yellowstone, and we were measuring the degassing directly from vents, but also through the soil. How much carbon are the volcanoes actually emitting? Because the climate skeptics keep telling us, no, this is the reason, right? And so there's us in the field processing data. But essentially, the conclusion was that anthropogenic CO2 emissions are about 100 times greater than all of Earth's volcanoes combined, okay? So this is how we can use geology, at least, to make sense of what's going on in the world around us. And the rate of that change is about 16 times faster than the fastest known rate of natural climate change that we have, okay? So this is why scientists, geoscientists are concerned about climate change, is that the rate of change is so dramatic. And if we keep going down this path, within 300 years, we'll have atmospheric CO2 levels of about 1,800 parts per million, which essentially takes us back to a greenhouse climate state. If you have a greenhouse climate state, sea levels are about at least 65 meters higher than they would be at present. Australia would regain its inland sea. Mar-a-Lago and much of Florida would be underwater. But unfortunately, populated regions like Southeast Asia, with hundreds of millions of people living around the coastal areas, would be most affected, okay? And then, these same climate change skeptics say that, well, we're being too alarmist, okay? You scientists, you're all so dramatic. It's fine, it'll all be fine. But this was the prediction from the year 2000 for fossil fuel emissions, and this is the actual data. And so we've been probably too conservative, and particularly when it comes to sea level change, this gray triangle from the year 1990 is what the IPCC projected, and then in colored is the actual measured observed sea level change, which essentially exceeds that envelope of projection. So there is a problem here. Same thing with atmospheric CO2. I don't really want to dwell on this. It's on the high end of our projections. But STEM science, earth science, is central to addressing many of these problems. So whether it's ensuring we have water, food, and energy security for a growing population, that we have some of these base metals and critical minerals to help us move to renewables, or actually also manage natural hazards. So for example, EVA's CubeSats, if you have a constellation of those, the idea is that, well, maybe they can detect the ignition of bushfires, and you send a drone out to extinguish the bushfire before it becomes out of control, right? So that we actually start to adapt to climate change, because it's fairly difficult to undo all of it. And then, of course, there's a lot of active debate about energy. Do we use nuclear? Do we use not uranium, but maybe thorium reactors? Chris is far more qualified to talk about that than I am. But what I'm trying to say is that the earth sciences do align a lot with the UN Sustainable Development Goals. So for example, hunger, we need to know where fertilizer is. How do we get fertilizer, right? Half of it is mined, and half of it is currently synthesized from natural gas. And this is the challenge I have, is, people say, oh, well, get rid of natural gas. Okay, but there goes half of your fertilizer to grow crops. And so who's going to suffer? And, these are very complex, wicked problems, and there are gray areas in amongst this. But I think science and STEM and earth science, again, give us hope to tackle these big problems. So we saw how COVID was treated in many places in the world. Science-informed policy making reduced deaths. Here is another example. A geochemist, a geologist, Claire Patterson, was using lead isotopes to figure out the age of the planet Earth. Using lead isotopes, but he discovered that lead pollution was everywhere. And of course, he linked it to industrial processes. And we knew back then that lead was a neurotoxin. And he himself launched an international campaign to eliminate lead from paint and petrol and other industrial processes. Now, he was demonized by industries. He lost his job at the university. He was just completely demonized. But eventually, and we're talking about like just 20 years ago, Australia phased out lead from petrol. We still have these huge problems of lead paints being eroded and washed out into our waterways. But Claire Patterson's basic research, which then led to this campaign, has probably saved millions of lives and changed the course of history. And same with the CFC refrigerants. Industry was like, yes, let's use CFCs. Of course, that caused the ozone hole. But because of science-based, science-informed policies, we could say, well, let's use something else, because now we can predict by 2050 that the ozone hole will close, and that will improve skin cancer rates and outcomes for the Southern Hemisphere. So STEM is the answer to this. Now let's quickly just talk about the energy transition, going back to some of my models that you can use plate tectonics maybe to predict where copper deposits are. Now the reality that we have is that electric cars use about 4 times the copper of petrol-driven cars. Each 3 megawatt wind turbine needs about 4.7 tons of copper, even greater amount of steel, 335 tons, even more concrete. Huge footprint of resources. And our economy, is ever more reliant on these exotic mixes of minerals. And of course, these minerals don't appear from thin air. They need to be extracted. So there's a wicked problem here that to get to net zero, we're probably going to need to mine more. But the key thing I want to point out here is that as we think about this, we need to think about ensuring that we're entering a circular economy. Because if we just mine things and use something once and throw it away, we're not really fixing the problem. We're just, shifting one problem elsewhere. So there's a lot of things to unpack here, and inequalities and whatnot. But here's just an example of copper discoveries through time since the 1900s. And we actually haven't found a lot of copper in the last 10, 15 years, okay, to actually sustain that renewable energy transition. And you might say, well, maybe we're not looking. And in fact, we're spending more than ever in terms of exploration. The reality is that the easy things have already been found at the surface. And so we need these sorts of models as well to look underneath the cover of sediments and so on to try to figure out where these might be. And so we've been looking at this in lots of parts of the world. So we tried to figure out, okay, well, what's the age of the subducting sea floor through time? What's the convergence rates? So on and so forth. I don't want to dwell on this, but that's just an example of how we can use these models for that. And maybe we need to think about energy and these problems differently. Maybe we need a paradigm shift. So for example, Australia could in fact become a renewable energy superpower. We could be exporting green hydrogen. Or here's another plan it's been talked about. It's not clear to me if it's going to get off the ground. But building a huge solar array with a 4,000-kilometer extension cord to Singapore to power about a third of that country. Okay, so there's radical thinking that we need to consider. So look, I'm going to wrap up here and just say that science is fun. There's still lots to discover. You don't need to be Einstein. You just need to be interested and passionate. And there's lots to be done. Earth science and other parts of STEM, of course, are helping us to address the biggest challenges that we face as a society. And tomorrow I'll delve deeper into the planetary carbon cycle. And I'd love to chat to you all more during the breaks. And please drop me a line if you've got any questions. So thanks for having me.